So welcome back. So the last lecture we had seen some motivations for definition of group, some examples and group action. So when you have a group, you have a set, one can make this group act on a set X, that's group action. And we saw the formula for number of orbits, and it turned out that number of orbits is precisely the average number of fixed points. Average number of fixed point meaning you take elements in G, consider number of elements in X which are fixed by G, and then sum it over divided by the size of the group. That's average number of fixed points. So before we move, let me mention to you certain examples of groups and actions as well, and these will lead for further discussion. So I will start with Sn. Yesterday I mentioned Sn is the group of permutations n symbols. So I have symbols say A1, A2, A3, An. I am permuting them, and then there are n factorial ways. So there are total of n factorial permutations. Therefore, the size of the group Sn is n factorial. The way the symmetric group is defined, the way Sn is defined, it's very natural that Sn acts on X. What is X? X is just the collection of those n symbols A1, A2, An. How does it act? So you take some element, I'll just call it sigma. Sigma is an element of Sn, and I take an element of X, say Ai. So sigma must be changing the position of Ai. It may be moving it to say jth place or whatever place. So then I take it to be Aj. So that is, sigma has a property that sigma permutes ith element to jth position. So that's how the permutation group is. Okay, so we have an action. What about orbit? What about number of orbits for this action? So that's not very difficult. Thing is, you see, Sn is collection of all permutations. Therefore, given any Ai and given any Aj, given any two symbols, so Ai, Aj arbitrary. So given any two symbols, there exists a permutation that moves Ai to Aj, right? So there exists with the property that when sigma acts on Ai, what you have is Aj, this property. And therefore, as you can see, number of orbits is just 1, because any point can move to any other point by action of Sn. Few more examples of groups I am going to mention. We shall need those groups in the lecture. Very simple group. It's denoted by Z mod 2Z or sometimes by Z2. What is this group? It's a group with 2 elements. When there are 2 elements, one of them has to be identity, other has to be non-trivial element. So I can say 0, 1, or I can say identity and some other element, say A. And what's the property? The property of the symbol A is 1 together with the group operation, I am calling it by star, 1 is 0. So star is, this is group law. In general, we have Zn, and this is called cyclic group of order n. What is Zn? Zn consists of, here I will take somewhat multiplicative notation, one element which is identity, the neutral element, and then some element A, and then you take operation of A with itself, take operation of A with itself, and once more, and you keep doing it until you do it this is n minus 1 times. So in the cyclic group there are n elements. So for the simplicity in notation, A star A, we just denote it by A to the power 3. This has notation A to the power n minus 1. So cyclic groups are quite simple groups, and there are some interesting actions of cyclic groups. In fact, a group which is as easy as this can be efficiently used in checking what I called yesterday parity. It can be used to see parity. We will understand that maybe in coming lectures. So with the parity we come back to Sn. There are 2 types of elements, there are 2 types of permutations in Sn. They are so called even permutations, and then they are so called odd permutations. The parity of even permutations is defined to be 0, parity of odd permutations is defined to be 1. So what is even and odd parity? So for that I will just devise some notation, and here I would call those symbols which are being permuted by the group Sn, I will just call them simply 1, 2, 3, 4 and so on. This is my x and my Sn is permutations of elements of x. So how to express permutations? So for that we are going to have a notation. For simplicity, just consider the case of say n is equal to 3. So this is the original position of these 3 symbols, and suppose after permutation you have something like 2, 3, 1. So what is happening here? 1 is going to 2, 2 is going to 3, 3 is going to 1. So I express it like this: 1 is going to 2, 2 is going to 3, and 3 is going back to 1. It's going back to 1, and that's all. There is no other symbol, and it's 3. So there is no fourth symbol. So this is how we denote this permutation. So this is a shorter notation, and yet another notation for this is simply 1, 2, 3, and we read it like 1 goes to 2, 2 goes to 3, and 3 comes back to 1. Let's take few other ones. Here let's take n is equal to 4. So let's see. Suppose this is the original position, and suppose 2 comes here, 1 goes there, 4 comes here, 3 goes there. That means after permutation, at the first seat 2 is sitting, second seat 1 is sitting, third seat 4 is sitting, and fourth seat 3 is sitting. So how do we express this? So notation for this is going to be, what happens to 1? 1 goes to 2. What about 2? 2 comes back to 1. And when we have complete cycle, we just close this bracket, and then we consider another symbol. So we can start with 4, we can start with 3. So I have 3, 3 goes to 4, and 4 comes back to 3. So I complete the cycle, and for the sake of simplicity, I just write it as 1, 2, 3, 4 as a notation. So simplest types of permutations are these. These are permutations. Simply you say 1, 2. That means two symbols are being swapped. So I have 1, 2, 3, 4, 5. Say for example, 5 symbols, and there I can consider 2, 3. What is 2, 3? 2, 3 is the one which takes 1, 2, 3, 4, 5 is there, which takes 3 here, 2 here, it just swaps, right? Swaps like this, and everything else is intact. So these spatial symbols, these spatial permutations which just swap two positions are called transpositions. So in fact, just by allowing two symbols to swap repeatedly, it's an interesting fact that we can construct all permutations. Just keep swapping, and that's how you construct all possible permutations. So repeated swapping creates all permutations. And in other words, the way we say it in the language of group theory, Sn is generated by transpositions. So for one transposition, for example, for this, how many swappings have happened? Only one, right? Only once you swapped. So if I take an element, for example, I am simply taking n is equal to say 3 and I am considering the element say 3, 1, 2. What is that? 3 is going to 1, 3 is going to 1, 1 is going to 2 and 2 is going to 3. So I am taking this permutation 3, 1, 2. I can express it as product of two transpositions. So I start with 1. What is happening to 1? 1 is going to 2. I just close it and then I write it like 1, 3. So 1 goes to 2 and here nothing happens to 2. So eventually 1 goes to 2. What happens to 2? 2 goes to 1 and 1 goes to 3. So 2 is going to 3. What's happening to 3? Nothing is happening here and here 3 is going to 1. So this and this they are same thing. First you perform this permutation and then you perform this permutation. So if you perform this permutation followed by this permutation, you will have the same effect. So 3, 1, 2 can be obtained by this product 1, 3 and 1, 2. How many transpositions are there? 2. So this is product of even number of transpositions. So permutation sigma is assigned parity 0 if it is product of even number of transpositions and it's assigned parity 1 if it is product of odd number of transpositions. One important thing, and it needs proof and I am not proving it, that this assignment is well defined. What's the meaning of that? The meaning of well defined is that if you have a permutation and suppose there are two different ways of expressing it as product of transpositions, and if one of the ways the number of permutations which are required, the number of transpositions which is required is even, then in any other way also the number of transpositions which will be required is again even. So it's the same thing, but that could differ. So this even number could be 4, that even number could be 6. That's quite possible. So this is well defined, and this map is called signature map, and for this lecture series I will be more often using the word parity. So parity is the word to express how many transpositions are required to express a permutation as product. Let's see few more examples of groups, and we lead those groups in coming lectures. So this lecture is full of examples. Let me tell you what Dn, these are dihedral groups. What dihedral groups are? Yesterday we had seen symmetry of rectangle. So today we are going to see symmetry of regular n-gon. So for n is equal to 4, the regular n-gon is square. So I simply take square So take this square and I just have some notation, say 1, 2, 3, 4. I can have various symmetries of this square. I can rotate it by 90 degree, I can rotate it by 180 degree, by 270 degree. I can also flip it, right? So let me denote R to be rotation by 90 degree in, let's say, anti-clockwise direction. And then with that I keep the notation R square to perform this thing, rotation 90 degree in anti-clockwise direction twice. So that is rotation by 180 degree. R cube would therefore be rotation by 270 degree. What about R to the power 4? That's rotation by 360 degrees, back to the same position. And for that reason we say that R to the power 4 is identity. So this 1 represents identity, doing the thing, the original position is back. What else can you do with this? You can actually flip it about x-axis. Yeah, it will again remain a symmetry. You can flip it about y-axis, that will remain a symmetry. You can flip it about diagonal, say d1, say this diagonal is d1, another diagonal d2. So you can do all these operations. So certainly the symmetry group of the square is going to have all these elements: 1, r, r square, r cube, fx, fy, fd1, fd2. F is for flip. In fact, as I said yesterday, composition of two symmetries is again a symmetry. So it would be a good exercise for you to think what is, say, R composed with, say, fx. You first flip it about x-axis and then you rotate it by 90 degree in anti-clockwise direction. What is it? Is it a new element which has not been explored here? No. So interesting thing is, if you try to compose all these things, you would realize this set is self-contained with respect to that composition, and therefore this is the group of symmetries of regular four-gon square which has 8 elements. In general, For n-gon, what we have is dihedral group, this name is dihedral group, and number of elements in the dihedral group of order n of of uh, the group of symmetries of regular n-gon, which dihedral group is, the order is, the number of elements is 2n. This has some contrast with the symmetries of rectangle, and I will just tell you what that is. So, you recall rectangular symmetry group, and here you have dihedral group. This group had the property, you remember, fx fy was same as fy fx. So, if you have a rectangle, you flip it by x axis and then flip it by y axis, it is same as first you do flipping about y axis and then you do flipping about x axis, the same thing. So, in fact, rectangular symmetry group, let me denote it by, here's actually notation. So, I will just stick to that notation. That notation is called V4, it's called Klein's 4 group, V4 notation. So, for every element in the group of symmetries of rectangle, we have that AB is same as BA. But if you take Dn and try experimenting it, if you take R and then you take, say, Fx, it's actually not same as Fxr. So, we first rotate by 90 degree and then flip about x axis. It's not same as first flipping about x axis and then rotating about 90 degree. So, when you have this property for a group, that for every element, for every pair, the order in which you are having the operation is immaterial, then this is called abelianness, this is called abelian group, while Dn is an example of what is called non-abelian group. So, abelianness is an important property of groups. Let me construct new groups out of given groups. Suppose G is a group, H is a group. So, two groups are given. You can take what is called direct product of G and H. What is that? Notation is G cross H. As a set, it is just a collection G comma H, just like what we have in Cartesian product. Just like that, G comma H, so the G is in G and H is in H, Cartesian product. And how do we take the group operation? How do we multiply two elements from this? So, this is one element G1 H1 and other element is, say, G2 H2. You simply take the first coordinate to be G1 G2, and where is it happening? We are having this operation in G, and then you have second coordinate as H1 H2, and where is it happening? It is happening in H. So, you can simply construct a new group out of two given groups. So, for example, if you have Z2, you remember Z2, it has just two elements. You take the Cartesian product with Z2. what are we going to have? We are going to have 0 0 0 1 1 0 and 1 1, and you of course know how to add them. So here if you add 0 1 with 0 1, answer is 0 0, and 1 0 with 1 0, answer is again 0 0. So here you should observe that what I had in Klein's 4 group, you remember there was a neutral element, there was one symbol fx, there was another symbol fy, there were meanings to these symbols, and then r pi. So as you can see, 1 corresponds to 0 0, fx corresponds to say 0 1, fy corresponds to 1 0, and r pi corresponds to 1 1. In what sense do they correspond? This is identity element here, this is identity element here. This has the property that it composed with itself is identity, this also composed with itself is identity. Same is true here, same is true here, like this. Moreover, when you compose fx and fy, you get r pi, you remember? Similarly, when you compose 0 1 and 1 0 in this fashion, in the sense of direct product, you actually get this one. In fact, all the relations which are there, all the group operation relations which are there are preserved when you make this kind of assignment. So this correspondence preserves group operations. Any map that preserves group operation is called homomorphism, and a homomorphism which is also invertible is called isomorphism. So therefore, Z2 cross Z2 and V4, they are isomorphic. A very interesting example of group that we are going to use to resolve one problem. You recall this? I had shown you last time the puzzle with the problem with the glasses, inverted glasses, how to change their orientation from all inverted to all upright, that problem. So that problem actually we are going to use a group, and I will introduce you to that group now. That group is actually Z2 cross Z2 cross Z2. What is that? Z2 is 0, 1. So here I have 0, 0, 0. So I am just taking once more the direct product exactly in the same fashion as we do it for Cartesian product. 0, 0, 0, so 0, 0, 1, 0, 1, 0, 0, 1, 1, and then 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, right? So these are 8 elements, and you have the group operation exactly in the same fashion as here. So for example, if I add 1, 1, 0, add meaning to the group operation, so 1, 1, 0 with 0, 0, 1, what I get is 1, 1, 1. So 1, 1 plus 0 is 1, 1 plus 0 is again 1, and 0 plus 1 is 1. So this is the group operation exactly what I had defined here in this same fashion. So this is group of 8 elements. All these elements have the property. So if, let me just say, if A belongs to Z2 cross Z2 cross Z2, then order of A, the A square is 1. So order of A is 2. Except for the identity element where A square is 1, but the order is just 1. So this group is what we are going to use in the permutation puzzle. So I hope you could understand this group, and I hope you could also understand that in Sn, when action is natural action is from 1 to 3 to n, the natural action of Sn, the number of orbits is and this is in some sense answering a question that I had raised in previous lecture, and this is going to be used in the next lecture when I try to answer the problem of making all 3 cups upright. So keep watching, see you.